Welcome to this explainer. I am absolutely thrilled you're here today because we're tackling one of the most brilliant foundational diagnostic tools in all of modern medicine, the electrocardiogram, or ECG. Now, for a lot of us, glancing at an ECG can feel a bit like trying to read ancient hieroglyphics. It's just a bunch of confusing squiggles on pink grid paper, right? Well, today we're going to change that entirely. By the end of this, we're going to treat the ECG not as a set of random lines to memorize, but as a readable, logical, and deeply visual language of the human heart.
I mean, think about it for a second. How exactly can 12 simple wires just taped to a person's chest reveal a silent heart attack, or a dangerous rhythm, or even a thickened heart muscle? It almost feels like magic, but it's actually just pure elegant physiology. We are going to completely demystify how these surface signals translate into a three-dimensional electrical map, giving us a real-time window into what's happening deep inside the chest.
Okay, here's our language decoder syllabus for today. First, we'll look at the heart's electrical system. Then we'll break down the basic waveforms. Next up are the 12 camera angles, followed by the genesis of a normal ECG, and we'll wrap up with diagnosing major abnormalities. Let's dive in.
Starting off with Section 1, the heart's electrical system, or what we can think of as the catalyst analogy. So before the heart muscle can even do its mechanical job of pumping blood, it needs a spark. We call that depolarization. This spark is literally the foundation of everything we record on an ECG, and it originates right up in the right atrium at the sinoatrial or SA node. And what makes the SA node so incredible is this property called spontaneous automaticity. It doesn't even need the brain to tell it to fire. It just initiates the normal heartbeat entirely on its own. From there, the depolarization wave sweeps through the right and left atria, almost like a ripple across a pond, telling those upper chambers to squeeze. Let's move along and see how their signal actually builds as it travels downward. From the SA node, the wave hits the AV node, and right here, something absolutely essential happens: a physiologic delay. The AV node deliberately slows the signal down for just a fraction of a second, which gives the ventricles time to actually fill with blood. Then, after that tiny pause, the signal just races down the His bundle and spreads rapidly through the Purkinje fibers. Think of these fibers as specialized high-speed conduction highways that ensure those massive ventricular muscles contract in a rapid, perfectly synchronized, and powerful squeeze. All right, moving on to Section 2, basic waveforms. This is basically the alphabet of our visual language. Now that we've got our spark and our pathway, let's map the waves you see on the paper to the actual cellular phases of the heart. The ECG waveforms are labeled alphabetically. We kick things off at 0 milliseconds with the P wave, representing atrial depolarization. Then, right after our AV node delay, at around 120 milliseconds, we get the QRS complex. That sharp, rapid upstroke corresponds to phase 0 of the cellular action potential, the massive ventricular depolarization. Finally, out at around 320 milliseconds, we see the T wave. That matches up with phase 3, the active recovery or repolarization of the ventricles, essentially resetting them for the next beat. Now, while we're talking about intervals, there's one measurement we absolutely cannot ignore: the corrected QT interval, or QTC. This captures both ventricular depolarization and repolarization. Since this time frame naturally changes depending on how fast your heart is beating, we have to use a mathematical adjustment, commonly the Framingham formula, just to standardize it. Why is this so crucial? Because a prolonged QTC significantly ramps up the risk of sudden cardiac arrest. Based on the source data we're looking at, the proposed upper normal limits are 460 milliseconds for women and 450 milliseconds for men. Let's jump to Section 3, 12 camera angles, and getting our spatial orientation down. If the waveforms are our alphabet, you can think of the leads as our perspective. Imagine you're directing a TV broadcast of a major sports game. You wouldn't just set up one camera, right? You'd place multiple cameras all around the stadium to catch every possible angle. That is exactly what a 12-lead ECG is doing. We've got two distinct sets of cameras here. First, 6 limb leads that look at the heart in the frontal plane, so top to bottom, left to right. Then we have 6 precordial or chest leads looking in the horizontal plane, wrapping right around the front and side of the chest. And here is the golden rule for all of them. If a wave of depolarization spreads toward the positive pole of a specific lead, that lead records a positive upward spike. If it moves away, you get a negative downward dip. Which brings us to Section 4, the genesis of normal ECGs, or what I like to call vector storytelling. This is where it all really comes together. We're going to combine our waveform alphabet with our camera angles using vectors, basically arrows that represent the mean direction of the electrical spread.
So the crucial point is how these vectors completely dictate the shapes on the paper. Let's take the atria first. The spread of electricity from the sinus node in the top right over to the left atrium creates a mean vector that points down and to the left. Since lead 2's positive camera sits down on the left leg, that vector is pointing right at it. Boom, we get a positive upright P wave. But lead AVR is sitting up on the right shoulder, so the vector is running directly away from it, which gives us a negative downward P wave. Now, the ventricular story is this fascinating two-part harmony. First, the intraventricular septum depolarizes from left to right. It's a short little phase, but it creates a tiny positive R wave in lead V1, which sits on the right side of the chest. Immediately after that, phase 2 kicks in, both ventricles depolarizing simultaneously. But here's the catch. The left ventricle is massively thicker than the right. It's basically the bodybuilder of the heart chambers, so it completely dominates the electrical signal, violently pulling the mean vector to the left and backward. For V1, this huge signal is running away, so we see a deep negative S wave. But over in V6 on the far left chest, it's charging right at the camera, giving us a tall, proud R wave. So, now you know the rules. You know exactly what normal looks like. But here is the critical question. What happens when this finely tuned electrical symphony goes completely out of tune? How do we actually spot the typos and errors in this visual language?
That leads us right into our final section, diagnosing major abnormalities and spotting those errors.
We're going to take everything we just learned about vectors and waveforms and use it to identify physical structural changes, things like enlarged chambers, thickened walls, and blocked coronary plumbing. Let's start with the top chambers, the atria. When physical changes happen, say an atrium gets stretched out from high pressure, it directly changes its electrical signature. If the right atrium is overloaded, it generates more voltage. That leads to a noticeably tall, peaked P wave, measuring 2.5 millimeters or more. We used to call that P pulmonale. On the flip side, if the left atrium is enlarged, the electrical wave just takes longer to get through it. That creates a broad, notched P wave, or a biphasic P wave in lead V1 with a deep, negative downward component.
And this brilliantly illustrates that the exact same principles apply to the massive ventricles down below. Hypertrophy just means thickened muscle, and thicker muscle cells generate way more electrical voltage. If the right ventricle is thickened, it fights back against the left, pulling the vector to the right and giving us an abnormally tall R wave in lead V1. But if the left ventricle is thickened, which we see a lot from years of high blood pressure, it generates massive leftward forces. You're going to see incredibly deep S waves on the right chest leads and massive, tall R waves on the left. In fact, if the S wave in V1 plus the R wave in V5 or V6 is greater than 35 millimeters, that is a classic hallmark of left ventricular hypertrophy, and that's a major, non-invasive marker of cardiovascular risk.
But beyond just muscle thickness, the ECG is our absolute frontline tool for detecting blocked plumbing, which we call ischemia. Recognizing severe abnormalities like a depressed ST segment or an inverted T wave, such as the deeply inverted Wellens sign that warns of a high-grade blockage, relies entirely on understanding that normal baseline we established earlier. The shift in these recovery waves is the heart's way of telling us the muscle is literally starving for oxygen. And when that oxygen starvation evolves into a full-blown heart attack or myocardial infarction, the rules become extremely strict. The universal definition for an acute ST elevation myocardial infarction, a STEMI, requires ST segment elevation of at least 1 millimeter in 2 contiguous leads. The chest leads V2 and D3 are so sensitive that the criteria actually vary based on age and biological sex. For example, it requires 2 millimeters of elevation in men 40 and older. We're also on the lookout for pathologic Q waves and reciprocal ST depressions in the opposite camera angles. Rapid identification here dictates immediate, life-saving reperfusion therapy, because when it comes to this, time is muscle. Now, with all these clear rules, you might be thinking a computer could just do this perfectly, right? But the source material leaves us with a pretty stark warning. It says, fully automated computerized ECG analyses still have major limitations, and therefore should not be accepted without careful clinician review. The human heart is incredibly dynamic. Leads can get misplaced, artifacts show up, and subtle structural diseases can mimic classical blockages. Advanced technology is amazing for sure, but human understanding of these core principles is still completely irreplaceable. Which leaves us with a really fascinating question to ponder. We've traced this whole journey from a tiny cellular spark to vectors moving in a 3D space, to diagnosing a silent heart attack on a piece of grid paper. But as technology rapidly evolves, do you think AI will eventually replace the human eye in reading this beautiful, complex electrical language? Or will the nuance and variability of the human heart always require a human touch?
Thank you so much for joining me on this explainer today, and I really hope you leave this wanting to explore even more about the incredible field of cardiology. Catch you next time.